So I'm going to talk about work with Soheyla, and she talked about it last term, I guess. But, you know, it's good to hear something twice, and I'll talk about it from a slightly different point of view. So non-abelian here refers to the, I guess, the gauge group. So this would mean, so another way of writing this title would be rank R DT theory from rank 1 DT theory. So the non-abelian would refer to GLR and the abelian to GL1. So I explain all the words in the title soon. So I'm going to, let me try and get rid of this floating meeting control. Okay, that's better. So I'm going to start off by reviewing DT invariants. But I won't give too much detail. I'll just tell you how to think about them. That will be an entire lecture course to explain them properly. And then I'll explain the rough idea of our work, which we apply in various different contexts in the 3 papers I mentioned on the first slide. So the rough idea is how we pass from rank R theory, counting sheaves in rank R, to counting sheaves in lower rank. And then I'll describe an example which is not entirely relevant to the overall project. So the overall project is to try and get from rank R to rank 1. But I'm going to explain how to get from rank 1 to rank 0. And the reason for that is because that works perfectly. There's no corrections. It works much more simply than all the other cases. And then I'll explain how to get from rank R to rank 0. So obviously that's just induction on this second point here. We pass from rank R to rank R minus 1 and lower. Unfortunately, we get all these corrections in lower ranks. So after we've applied it R minus 1 times, we get down to rank 1 and rank 0. So we don't just get to rank 1. So then we apply it one more time, and that gets us down to rank 0. So now we have all of DT theory expressed in terms of rank 0 DT theory. I'll explain what all that means. Then I'm going to explain a little bit about the proofs and the technicalities that go into it. And then finally, I'm going to explain how we go from rank 0 to rank minus 1. And that is essentially equivalent to rank 1 up to a certain shift and dualization, as I will explain. And so what that does is it gets all ranks expressed in terms of rank 1 DT theory, which is what we really want, because rank 1 DT theory is the theory that's been heavily studied and that counts curves on your Calabi-Yau threefold and is equivalent to Gromov-Witten theory, as I will explain. Okay, so any questions? You're not meant to understand this, but so I won't allow questions. I'll begin. So I'm going to work on a Calabi-Yau threefold throughout with a fixed line bundle. That's to measure stability of sheaves. If you change the line bundle, there's a wall crossing formula, but you get equivalent results. This line bundle is not so important, or the dependence on the line bundle is controllable. And there'll be a technical assumption, which I'll explain later, that the Calabi-Yau threefold should satisfy the Bogomolov-Giesecke inequality of Bayer-Macrì and Toda. Fortunately, our results aren't vacuous, because Chunyi Li has shown that on the quintic threefold, most of the stability, well, all of the stability conditions that we will use satisfy this conjecture. So that's good. And more preliminaries, I'm going to fix a Chern character throughout, or a numerical K-theory class. So this is going to be the topological class of my sheaves that I'm going to count. And I'm going to count semi-stable or stable bundles or sheaves or complexes of sheaves in this class. And that's what DT theory does. But before I get there, I have to say something about stability. And most of the participants in this seminar know more about stability than I do. So this will be, so I apologize for this. You can usually write it in terms of some complex number, which depends only on the topology of the sheaves we're interested in. So that's C, that Chern character. And then if you write this complex number in its polar decomposition, you get this angle, and tan of the angle, or the slope of the complex number, is the thing that's relevant to stability. And it's the standard definition. Once you have a notion of slope, you ask that something be stable or semi-stable, according to whether this inequality is strict or non-strict. And it's that the slope of sub-objects should be less than the slope of quotient objects. And for the slopes we consider, that will also be closely related to and imply that the slope of the sub-object is less than the slope of E. And then the tricky bit comes in what you mean by a sub-object. But for now, you should think of sub-sheaf. But that won't always be the case, because we'll work in fancy exotic abelian categories, because we'll work with complexes of sheaves and so on. And so what you mean by sub-object is part of the data that goes into a stability condition. But for now, we can ignore that. Let's just pretend we're dealing with some topological notion of slope, and slope of sub-objects being less than slope of quotient objects is what defines stability. And so you should think, obviously, of Mumford's slope, the original slope stability, where your real and imaginary parts are the rank of the sheaf and the degree of the sheaf, measured with respect to the first Chern class of our line bundle. So that's where this H is entering in. Okay, so that gives the usual slope stability. And then, you can concoct, this is a bit, what's the word? This is a bit forced, but anyway, you can also take Giesecke stability, where instead of just taking this degree of the sheaf, you can take the degree of the sheaf to leading order, and then some terms depending on the second Chern class, its third Chern class, and so on. And again, divide by the rank, and that gives you Giesecke stability. But its exact form really doesn't matter for now. Just think of usual mu stability on curves. Okay, so there's going to be notions of stability. And then DT theory is where, or at least this is the old DT theory of 25 years ago, is where you make this simplification that there's no strictly semi-stables. Okay, so I'm going to work with Giesecke stability for now because it's better for algebraic geometry. Later we'll change that. But let's assume that if anything's semi-stable, then it's stable. That's a simplification. We drop it on the next slide, but this is what the theory looked like many years ago. And in this circumstance, we get an integer, the DT invariant, counting Giesecke stable sheaves of our fixed class Chern character C. And some of the details are that the moduli space of objects, of stable objects of that class, is firstly projective. It's compact because there's no semi-stables. And it has something called a perfect obstruction theory of virtual dimension 0. And either you know what that is or you don't. And I'm not going to change that today. But roughly speaking, what that means is that firstly, you have deformations of sheaves. It's a statement about the deformation theory of the sheaves in this moduli space, or in other words, the deformation theory of points of this moduli space. So for starters, we have a Zariski tangent space. That's first order deformations of our sheaf. That's given by x1 EE. Maybe you take trace free if you fix the determinant. Dual to that, by Serre duality using the Calabi-Yau 3 condition, you find that the obstructions to deforming sheaves lie in the dual space to the tangent space. So they lie in the cotangent space. And by the same Serre duality argument, there's no higher obstructions. So x3, for instance, is Serre dual to Hom, and there's no trace-free Homs because my sheaves are stable, and so they're simple. They have no automorphisms, only scalar automorphisms. And then there's no x4s and so on. Okay, so because there's only deformations and obstructions, there's only x1s and x2s. That means we get a perfect obstruction theory after a lot of work. And because the deformations and obstructions have the same dimension, their difference is 0, and that's what this virtual dimension 0 is. So what that means is, morally speaking, the moduli space ought to be 0-dimensional. In reality, it won't be. It'll be higher dimensional and singular and so on. But it ought to be a finite number of points. if you could perturb things, which you often can't because you're in algebraic geometry and it's rather rigid, but if you could, you would expect the moduli space to split up into a finite number of points, and then the DT invariant would be that number of points. And even though you can't do that, you can produce some replacement for the fundamental class of the moduli space. So that's called the virtual fundamental class, and that will be a zero-dimensional in this case, because the virtual dimension is 0. It'll be a zero-dimensional homology class or Chow class on the moduli space, and you just take its degree. It's the number of points in that zero-dimensional Chow class is the DT invariant, and it can be negative. So that shows you one reason why you might not be able to perturb things to break things up into a finite number of points. All right, so that's the DT invariant. There's a cryptic statement if you're a math, that's more physicists. But maybe what I will say is that the local model of the moduli space is that it looks like the critical points of a function on a smooth ambient space. And so it's the zeros of a closed one form on a smooth ambient space. So that's why you expect the dimension of the moduli space to be 0, because you've got the same number of equations as unknowns, because if your ambient space is dimension n, then your one forms have rank n, and so you've got n equations and n unknowns. So just as in Moore's theory, you expect the critical points to be isolated, and then you count them, and that's your DT invariant. Okay, so roughly speaking, you're trying to take the Euler characteristic up to sign of your ambient space. Okay, and for this and other reasons, it makes sense to think of this DT invariant as the topological Euler characteristic up to sign of the moduli space. So it's not quite that. When the moduli space is smooth, this formula is precisely correct. And more generally, there's a way of generalizing this formula to make it correct. So Behrend assigned a multiplicity function, a multiplicity to every point of the moduli space, which is an indication of the singularities of that point of the moduli space. So if that is a smooth point of moduli space, the multiplicity function is just this sign. It's just plus or minus 1. But if you had a fat point, if your moduli space was a fat point, then the multiplicity you would assign to that point is the usual scheme theoretic multiplicity of that fat point, the length of that zero-dimensional scheme. So when you then take Euler characteristic, instead of assigning 1 to that fat point, you assign its multiplicity, and you get the length of this Artinian zero-dimensional scheme, as you might expect. And so Behrend showed that the DT invariant is given by this weighted Euler characteristic, where you take the Euler characteristic of the moduli space weighted by this multiplicity function. All right, so you're not meant to absorb all that. You're meant to think throughout this lecture that the DT invariant is the topological Euler characteristic of the moduli space. It isn't quite, because that wouldn't be deformation invariant, but there's a way of mucking with that naive definition to make it deformation invariant. But for the purpose of this talk, it'd be better to just think of it as the Euler characteristic of the moduli space. Are there any questions about that? Okay. And now we want to drop this condition that all the semistables are actually stable. We want to allow strictly semistables. And these objects are more difficult to count, essentially because the right way to count them would be to take 1 over the Euler characteristic of their stabilizer groups. But the stabilizer groups have 0 Euler characteristic. So you get infinity. So you need a way of kind of regularizing that. So Joyce and Kontsevich-Soberman found a way of doing this. So yeah, I should explain first. So suppose you have a stable object, smaller charge, like say C/2, Then you could take direct sum of it with itself or with another object of charge C over 2. And extensions, self-extensions, to get semi-stable objects of charge C, but with larger automorphism groups. And you can think of this procedure here as being related to some kind of exponential. So if you take n copies of E, then there's a symmetric group of n letters acting. So that has size n factorial. So you might want to count that with a 1 over n factorial. Or more generally, if you take n copies of E, you get a GLN, if all the E's are stable, you get a GLNC automorphism group, and the Weil group is n factorial. So you might think, so you can see that 1 over n factorial plays a role. So you might think of this as some kind of exponential. And Joyce and Koncevich-Soyberman took some kind of logarithm to invert this process, or partially invert this process. And it's a complicated theory, and this talk isn't about that, so I'll leave it at that as a mysterious comment. And once they've taken this logarithm, what they end up with is something which is better behaved. This ameliorates the automorphism groups. It makes them better. So it's like, instead of counting all these guys like E plus E and E plus E plus E and so on, you just say, well, they already came from E, so I threw those away, because I already understand those. They're already embedded in the count of E, in the count of objects in Chern character C over 2 or 3 or 4. So I throw those away, and then I end up with something much better. It behaves much better. That Koncevich-Soyberman conjectured that. Joyce proves that in the setting that he worked in with Song. And so him and Song were able to make a rigorous definition of a numerical invariant. So this is the generalized DT invariant, and we call it J of C. It's a rational number now, it's not an integer anymore. But when you have no strictly semistables, it reduces to the previous integer from the previous slide. And it has two properties. One, it's invariant under deformations of X. But as I say, you should think of it as just as the topological Euler characteristic of the moduli space. That doesn't have this invariance, but you can modify that slightly to make it behave this way. And then it isn't invariant under changes in the stability condition, like changes in the polarization, the Kähler form. But how it changes as you deform the stability condition is controlled by a precise wall crossing formula. So that's the nice properties of this thing. And then Koncevich-Soyberman produced a more elaborate theory, much more complicated, producing more refined invariants like Laurent polynomials or rational functions, motives, and all kinds of fancy stuff. Their theory was partly conjectural at the time. Most of it's now been proved by people like Meinhardt and Davison. And so probably most of what this talk is going to be about goes through for their more elaborate invariants as well. But I'm going to talk purely about this Joyce-Song number, this generalized DT invariant. All right, so any questions about that? All you need to know is there is an invariant and it satisfies certain rules, it has certain behaviors, and you should think of it as the number of sheaves of a fixed Chern character. Or you should think of it as the Euler characteristic, the moduli space of sheaves of that fixed Chern character. You won't go wrong if you stick to that. So now I want to explain the simplest possible wall crossing formula to give you a feeling for this, and because we'll use it later on. So suppose your bundle or sheaf sits in an exact sequence like this, and we're going to vary the stability condition, so maybe the Kähler form or the polarization, so that the slopes of A and B cross each other. Okay, so in the space of stability conditions, we'll have a wall on which the slopes of A and B are the same, And then below the wall, the slope of A will be less than the slope of B. So F will be stable. And above the wall, F will be unstable, but extensions in the opposite direction will become stable. And this is a very simplified setting because I'm assuming A and B themselves are strictly stable throughout. They themselves don't get destabilized as we move around in the space of stability conditions. That would lead to a more complicated wall crossing formula, which I'll come back to. So this is the simplest wall crossing formula. I'm also going to assume A and B aren't isomorphic to each other. Again, when they are isomorphic, there's something else you can do, but it's more complicated. Okay, so as we cross the wall, in the moduli space of stable objects, F, we lose a projective space of all possible extensions from B to A. And we gain the projective space of all extensions in the opposite direction. And we don't have any control over either of those. They can be enormous or small. But Riemann-Roch gives us control over their difference in some sense. So the topological Euler characteristic, what happens to that? Well, the topological Euler characteristic of the projectivization of a vector space is just the dimension of the vector space. So we lose this topological Euler characteristic, the dimension of this vector space. That's the topological Euler characteristic of this one, projective space. And we gain the topological Euler characteristic of this guy. And by Sayre duality, this second x1 is dual to this x2. And so what we end up with is x1 BA and x2 BA and their difference. And this is given by Riemann-Roch formula because this is the alternating sum of all the x's. All right, because I'm in a situation where, let's say A and B are sheaves, so there's certainly no negative x's. Therefore, by Sayre duality, there's no x's in dimension 4 and above, in degree 4 and above. Also, I assumed that A and B were not equal, so there's no HOMs from A to B or from B to A. Because they have the same slope on the wall, and slope stability has this sort of Schur property that if you have a HOM between objects of the same slope, then it's an isomorphism. So there's no HOMs from A to B or B to A, therefore by Sayre duality, there's no x3s either. And so actually this is the alternating sum of all x's. So it's given by a topological formula, and it's called the Mukai pairing between A and B. So it's given by Riemann-Roch, the integral over x of the Chern character of B dual times the Chern character of A times the tog class of x. Okay, and that was just for a fixed A and B. Now I can vary the A and B's over their moduli space and see what happens and sum up all these Euler characteristics. This Euler characteristic computation I've done here. This is the Euler characteristic of the fiber, and then I move in the space of A and B's, and I take the Euler characteristic weighted by this contribution. And this is the formula I end up with. So this says that the DT invariant above the wall in the class of F, that means its Chern character or its K-theory class, is the DT theory below the wall, plus the correction. We're ignoring the sign as usual. The correction is this one here, is this change in Euler characteristic of the fibers. That's this Mukai pairing between A and B, that's topological. And then as we move over the space of A and B's, I get the Euler characteristic of the moduli space of A's and the Euler characteristic of the moduli space of B's. And when you put in the Bayer function, you make this all correct, you get the same formula. So this is the simplest wall crossing formula. So this is kind of crucial to everything we do. Are there any questions about this? You're a very quiet bunch. And then the more complicated wall crossing formulae are much more complicated, but they have the same general shape. Here this was the contribution coming from splitting F into sort of two pieces or having a filtration of F length 1. We can also get splittings into 3 pieces, 4 pieces, longer filtrations with associated gradients of many pieces. They just give us, instead of a quadratic in J, they give us cubic in J when you have 3 pieces, quartic in J when you have 4 pieces, and so on. And they have the same shape. what comes outside is some universal coefficient times by something topological involving only the Chern classes of the pieces which arise, times by a dt invariant of each of the pieces. So it has the same shape, it's just instead of being quadratic, you get cubics, quartics, and so on. And that's all we need about the wall crossing formula. Yes?
So I may ask a question that
yeah.
So what happened on the moduli level? Is that true that is something like we remove some locus of a Pn bundle and replace it by another Pn bundle?
Yeah, I mean, of course, it's a stratified Pn bundle, and it might be the whole space. Everything here is virtual, so it might not be a birational thing that's going on. It's only virtually birational. And in fact, one can analyze all this. You'll like this. So one can analyze all this at the derived category level, and Toda has started doing all that kind of thing. So he's produced a categorification of this wall crossing formula, where you have the derived category above and below the wall, and you see how the derived category changes, and then this gets replaced by some semi-orthogonal decomposition.
Thanks.
So do I understand right? If you know, let's say some Jordan-Helder filtration of your strictly semi-stable object, then from that you can sort of write down the formula? Or how does it?
Yeah, you can write down part of the formula that relates to that object. So yes. Yeah, that's right. If you're on the wall and you have some Jordan-Helder filtration, then that will give you a term in this wall crossing formula. But there'll be other terms coming from other possible decompositions of your class. So even though your sheaf might not have another Jordan-Helder filtration with different classes, some other sheaf in moduli space might. So actually you'll have to sum it, just as here, actually, I've missed out a summation over all classes A and B, which add up to the class of F. Similarly, the answer to your question is yes, after you add in a sum over all possible decompositions. Is that okay?
Yeah.
Yeah, great. Okay, so then the rough idea of what we do is the following. So first of all, we just twist up all our, we're going to consider sheaves to start with. So we're going to consider sheaves in a fixed Chern with fixed Chern character C. Okay, and then we fix some n that's huge so that all our sheaves have no higher cohomology. And now we're going to replace E by the co-kernel of a section of that twisted sheaf. All right. So there's the exact sequence. And now this F, this co-kernel that we produce by by dividing out by a section, obviously has rank 1 less, and we know what its Chern character is. And to a first approximation, you should pretend, for now, for this slide, that all these E and Fs are stable. There's no issues. As long as the section's non-zero, the co-kernel's stable. And if I gave you an F and an extension like this to O minus n, then you should assume that E would be stable as well. So that's not true in general, but let's assume it is for now. Then, because this n is very large, it turns out that all the Fs come from the E's. So if you start deforming this sheaf F as an abstract sheaf, forgetting about E, turn out that whatever you deform it to will also have a presentation like this for some other E. Okay, and that's because n is so huge. So all the Fs come from the E's. And so the moduli space of Fs here is actually a projective bundle over the moduli space of E's with fiber, the projectivization of the space of sections here. So because F has scalar automorphisms, sorry, I'm talking about the extensions now. Obviously, if I scale S, I get the same sheaf F, but because E, I'm assuming is stable and has no automorphisms except for scalars, then anything else, any other way I change S will give me a different F. But of course, if I just scale S by a scalar, it will give me the same F. So what I get is not the space of sections, but the projectivization of the space of sections. That's my fiber of the moduli space of Fs over the moduli space of Es. And so what I end up with is, to a first approximation, that the dt invariant of counting Fs is the dt invariant counting Es times by the Euler characteristic of the fiber, this Pn-1 bundle. So that's just an n, where n is the number of sections. All right. It's just this topological number because remember I twisted up so there's no higher cohomology. So that's the key idea to everything we do. The reality is, of course, F needn't be stable, E needn't be stable, and what we do is we find a stability condition for which more or less they are both stable, and then we wall cross until we get to the stability condition which we're really interested in, which is maybe Giesecke stability for E and F. So that will produce all kinds of corrections to this formula, and then the game is to try and control those corrections. But this is the rough idea of everything. This is what replaces rank R sheaves by lower rank sheaves, here rank R -1. And as I say, later we'll get corrections from even lower rank. And what else did I want to say about it? Yeah, this is, if this weren't just an approximation, if this were really true, then we'd be done. We'd have expressed the rank R dt invariant here, J of C, as a universal formula in terms of rank R -1 invariant J of Cn. Oops. And then we have to wall cross to handle stability and get the correct formula. Any questions about this? This is the key slide, really.
So this sequence should really give you a wall for F and not for E when you do it in some kind of stability condition.
Ah, yes. You're an expert. That's cheating. Yeah, we'll get to that. That's correct. And that's unfortunately why we have to work with complexes of sheaves and not in the usual abelian category of coherent sheaves. Okay, we come to that later. Okay, so the first example is passing from rank 1 to rank 0. And here everything works perfectly, which was a big surprise to us, I must say. This isn't obvious at all. But let me just state it. So first we start in rank 1. So we take this moduli space of sheaves with Chern character C, where C is rank 1. This is a moduli space of ideal sheaves. So after tensoring by a line bundle, all your stable or semi-stable sheaves, firstly, all the semi-stable sheaves are strictly stable, so everything's good. And secondly, all the sheaves are just ideal sheaves of subschemes of X, and they're curves and points in X. And then what's one of these sections? Well, it's a section of this ideal sheaf twisted by n. Well, you can ignore the ideal sheaf. That's therefore also a section of O of n, and so it cuts out a divisor in the linear system, in the ON linear system. So what this data gives you is a divisor, and then the fact that it lifts to this ideal sheaf means that the section vanishes on Z. So Z is inside the divisor. So actually what these Fs are is, roughly speaking, pairs, a divisor in the linear system ON with a subscheme Z of dimension less equal 1 of that divisor. And what the actual sheaf F is the co-kernel of this section, is it's the ideal sheaf of Z considered as a sheaf on the divisor and then pushed forward to X to give a rank 0 torsion sheaf on X. So the sheaf is 0 on most of X. On D, it's the ideal sheaf of Z. And this is an object called in physics a D4, D2, D0 brane, and physicists make predictions about these things. I'll come back to that. And in this case, amazingly, E and F are Giesecke stable, slope stable. There's no semi-stability. There's no nothing. Everything works perfectly. And they're the only stable sheaves of this form. So everything works perfectly. The moduli space of these torsion sheaves here is a projective bundle over the moduli space of the original ideal sheaves. And therefore the DT invariants are given by an impossibly simple formula. They're equivalent to each other. And there's nothing else that happens. So, this last comment is, here's something that might have happened that I personally expected would happen. And that would happen if n was small. But for us, because n is so large, this doesn't happen. So imagine you took a divisor in half the linear system. So a divisor is sort of half the degree. Then you can do two things. You can either stick a rank 2 bundle on it instead of a rank 1 bundle like here, and then push it forward. Or you could take the rank 1 bundle given by, pushing forward structure sheaf or ideal sheaf from twice the divisor, the scheme theoretic thickening of the divisor. Only the second thing can happen. The first thing, putting a rank 2 bundle on this D, will always give something unstable. So the only thing that happens is that you get these sheaves which are rank 1 on their support. And that's because n is very large. And that's a consequence of this Bogomolov-Giesecke inequality. So that's extraordinary, to me anyway. And so we get this very simple formula. There's no corrections. Life's good. And both sides are interesting. So there's the formula again. So on the right-hand side, the rank 1 invariants, these are what count these ideal sheaves of subschemes of dimension less equal 1. So curves and points on X. And they're the things that people usually mean by DT invariants, these rank 1 DT invariants. These are the subject of this Malik-Nekrasov-Kukov-Pendra-Panda conjecture. And they can be written in terms of the Gromov-Witten invariants of X conjecturally. And that's now been proved for most Calabi-Yau threefolds like the quintic threefold. So on the right, we essentially have Gromov-Witten invariants. On the left, we have these D4, D2, D0 branes. And the counts of those are conjectured by S-duality in physics to be vector-valued modular forms. And I won't have time at the end. This is for when I gave this talk to a bunch of curve counters, but you guys don't care about Gromov-Witten invariants. So I won't labor the point at the end, but we discuss in one of our papers this conjecture and how it might be useful. So this hasn't really been exploited in maths, the idea that Gromov-Witten invariants might be controlled by modular forms, but there's a great deal of problems with that, and it's a long way off. It's still a long way off. So I won't say more about that. So that was a digression. So let me get back to what we really care about, which is writing rank R invariants in terms of lower rank. Okay, so now we get corrections, and that means we write the rank R invariants in terms of rank R-1 and all this kind of shrapnel in lower ranks. And so inductively, you can get to rank 0 and you prove this result. That's probably the second paper on the first slide. And it says that DT invariant in rank R can be written as a universal polynomial in DT invariants of lower rank, of rank 0. So these are these things that are supposed to be governed by vector-valued modular forms. And this is some kind of polynomial with infinitely many entries. But if you evaluate it on any fixed Calabi-Yau threefold with a fixed C, then only finitely many of those entries will be non-zero. So it's a sensible formula. So it's a polynomial in countably many terms. Okay, most of which are 0. All right, so what that leaves is to try and express the rank 0 theory that we got on the right here in terms of rank 1, and I come back to that at the end. So I want to talk about now how we do this, so what the technicalities are. And it all comes down to these weak stability conditions of these unknown people here. And for us, these stability conditions are going to depend on two parameters, B and W, real numbers. W has to be bigger than half B squared. And we have to work in this exotic abelian category, which is a tilt of the usual abelian category of coherent sheaves. And most of this audience don't mind that kind of thing. But if I give this talk to different audiences, I have to apologize at this point. So anyway, these are two-term complexes of sheaves. These are rather easy to motivate using tilts, but I don't have time to talk about that. But in this abelian category, certainly our sheaves, for instance, E-1 might be 0, and then you would just get a sheaf E0 in degree 0. This is the abelian category that Bayer-Macrì and Toda work in, and it turns out to be absolutely perfect for what we want to do. You'll see why very shortly. It's related to Benjamin's observation that we really need two-term complexes for what we're doing. But you'll see that in a minute. And then there's some slope, some central charge and a slope. And you shouldn't really look at these formulae. Just all you should notice is they're topological. So they only depend, again, on the polarization, on the Kähler form, and the Chern character of your sheaf or complex of sheaves. And the one thing to notice in this formula is that they only use rank, first Chern class, and second Chern class. They don't use the third Chern class. And this is reminiscent, and that's the origin of the name weak. And this is reminiscent of slope stable sheaves on, let's say, surfaces or higher dimensional things. Slope stability, usual Mumford slope stability, only depends on the rank and the first Chern class. And yet the Bogomolov inequality says that it gives you a bound on the second Chern class. So if you're slope stable, at least, then the Bogomolov inequality says your second Chern class is roughly, I can't remember, positive or negative. And so you get a bound on the second Chern class from stability defined using only the rank and the first Chern class. So here we have the Bogomolov-Giesecke conjecture of Bayer-Macrì Toda is sort of one up from that. It says that for objects which are stable with respect to this slope on this abelian category, we have a bound, even though the slope only uses rank, first Chern class and second Chern class, we have a bound on the third Chern class. So that's this Bogomolov-Giesecke conjecture. And, you know, there's the inequality, and you're not supposed to absorb it. You can see it depends on the BMW. And it gives you an inequality on the third Chern character. And they invented it because it's sufficient to prove the existence of Bridgeland stability conditions. But that barely comes into what we do. But that's why people have studied it and why Chinese proved that these things, that it's satisfied for many B and W on the quintic. Okay, so now I want to say how this wall crossing goes. And it goes like this. So we plot the some information about the Chern character of E on a two-dimensional graph, and we superimpose on the same graph the B and the W, which tell us which stability condition we're using. H is fixed for us. Okay, and you get pictures like this. So I have to talk you through this. So inside the parabola, the gray area, that's our space of stability conditions. You pick a point in here like BW, that gives you a stability condition. Outside the parabola is where the semi-stable sheaves lie. So the Bogomolov inequality tells you that this point here, this slope-like object here, lies outside the parabola. And then if you join your stability condition to your object, your Chern character, E, then the straight line joining them, its slope is the slope of your of E in the stability condition BW. So this, where is it? This new BW here, this slope here, that is the slope of this straight line. Okay. And so where do you get wall crossing? When do you get walls of instability? Is when there's some other object like F, which also is on this line, because then it's slope of F and slope of E are the same. So it's possible that F might destabilize E if there's an injective morphism in this abelian category from F to E. So this is the picture you get on a wall of instability. And then if you move B and W, you know, just below this line or just above, it will lie in a chamber where stability doesn't change as you move within this chamber. Nothing remains stable or unstable. Nothing changes. And then you'll cross other walls. Okay, so this is the picture. And the picture for us is the following. We're going to consider, as Benjamin pointed out, we're going to consider stability of the Fs. So this class Cn. So these are the co-kernels of our sections. But I'll come back to that in a minute. And then we get a picture like this. So our Fs live down here, the bottom right-hand corner of our picture. And you can try and analyze their walls. We don't know too much about them, but what we know is, firstly, there's only finitely many of them. There's a lower bound to them, which I shouldn't have called a wall, this Bogomolov-Giesecke line here. Below here, any object of class Cn has to be unstable by the Bogomolov-Giesecke inequality. So we know down here our invariance is 0. Then there's a finite number of walls. One of them is red. We know that. We call that the Joyce-Song wall. That's the wall that joins our class of F to our class of O minus N, that line bundle that I used earlier. So that'll be the wall on which O minus N and the F have the same slope, and that'll be the wall on which these pairs that I was talking about become relevant. I'll explain that in a minute. And then there's some finite number of walls above that. There's some uppermost wall, and then you're into this region called the large volume region, where everything's good. So everything up here is something called tilt semistable, where tilt is something in between Giesecke and Mumford's slope. Mumford's slope uses the second term of the Hilbert polynomial. Giesecke uses the second and all the higher ones. If you just use the second and third, that's tilt semistability. But anyway, up here, everything's a sheaf. It's damn nearly semi-stable in a classical sense of Mumford's slope or Giesecke. And we know how to wall cross from tilt semistability to Giesecke or slope. Joyce already worked that out. And basically, if you get up here, you're done. Okay, so the game is to go from down here where we understand everything's 0, to up here where the invariants are the invariants we're after. Roughly speaking, the invariants counter Giesecke semistable sheaves. And as we cross the walls, all kinds of mess happens. As we cross the red wall, we get the formula we want. That's the rough idea slide. And all the other walls are going to generate corrections. And then the game is to control those corrections and say they're small in some sense. And the sense in which they're small is maybe that they have lower rank and lower discriminant, but we come back to that. Anyway, any questions about this picture? Okay, so yeah.
Will the number n play a role in this? Picture?
No, it's just fixed and large.
Usually large.
Yeah. So the Joyce-Song wall is where the slopes of the Cn or the F and this actually the shift of this O minus N line bundle are the same. And so what happens there is, you remember that exact sequence we had, rotating that in the derived category, we write this as an exact triangle. And this is an exact sequence in that abelian category that we're using, Bayer-Macrì and Toda. Okay, so the original exact sequence of covariant sheaves is not an exact sequence in the abelian category we're in, but this is. So this is the only place we really need two-term complexes. Okay, so O minus N shifted is a two-term complex. You know, it's in the wrong degree to be a sheaf. So these are the triangles that are showing up on that red wall. So below the wall, F would be destabilized by such a sequence, and above the wall, it wouldn't be, it'd be stable. Okay, there's the precise conditions here. And what this gives is a wall crossing formula, very similar to what we've seen before. So it says the Joyce or generalized DT invariants above the wall, where W is slightly above a W on the wall, are equal to the invariance below the wall plus the correction. And what's the correction? Remember, it's the difference in extensions between this one and this one. So this line bundle and E, and the ones in the opposite direction. So it's the Mukai pairing between these two objects. Okay, and what that is just the sections, the number of sections of E twisted by N, because the extensions obviously from this guy to this guy are just the same as the maps from O minus N to E. So this is just exactly the term we saw before when we said the space of F's was a projective bundle over the space of E's. What we're getting here is something slightly more complicated with more corrections. Okay, so there are then corrections because E or F might be destabilized, sure, by E, but then E in turn might be destabilized by something else. Maybe E is a direct sum of two things with the same slope. And you get these complications with the section. Does it lie in E, or does it actually lie in a semi-destabilizing subsheaf of E? You have to sort of subtract off terms from that. There's an almighty inclusion-exclusion principle going on. So there's higher corrections because nothing works just as we want it. Okay, but this is the wall crossing formula you get. Okay, so this is the term we saw before, and it really is just a wall crossing formula. All right, and again, the game is to control these higher order terms and show they're smaller in some sense. They come from terms of lower rank. So I'll come back to that. And then from this formula that we get from crossing the red wall, what do? We take the terms above the red wall, so like this one on the left here, we take them up to infinity to try and wall cross them until they just become counts of Giesecke semistable sheaves, F. And we take the terms below the wall, like this one, down to below the BG line where they become 0. And we see as we do that, what changes occur, what corrections we get to this formula, and we try to control those corrections and show that they're all of lower order terms in some sense. So that's the game. So how do we do that? Like, what control do we get? Well, what you do is using that BG inequality, using one key thing that Soheyla taught. You know, as you move along this wall here, these objects, E and F, if they're semi-stable, let's take E, suppose E is semi-stable, and I'm on a wall here. As I move B and W along this wall, this is a very long wall inside this parabola because N is huge. And E has to remain in the abelian category all the way down here as I get towards one edge of the parabola, and all the way up here as I get very close to the other edge. And because it lies in this abelian category here, I get inequalities here for B very small and B very large in this picture. And they give us control. And putting together that and the BG inequality, you get the following control. Where was it? Where was I? What it turns out is it's very easy to prove using, not very easy, that's incorrect, but using those two inequalities, it turns out you can prove that any other wall crossing for very large N, remember, involves only sheaves. The semi-stable objects are sheaves, they're destabilizing sub-objects are sheaves, the pieces they split into are sheaves, okay? The only place you don't get sheaves are in this extreme case where you get this shifted line bundle on the Joyce-Song wall. That's because that really lay right on the parabola. I think I had a picture of that, didn't I? Yeah, that really lay right on the parabola. Everything else lies just off the parabola. You take N large enough, use these inequalities, and you can just show they can't happen. Okay, so and then all these wall crossings spit out, you know, higher order terms, destabilizing pieces, which are sheaves. And then we wall cross those as well. So they give us terms, they give us counts in a certain stability condition. We then wall cross those until they give us counts of sheaves. And we see what corrections we get as we wall cross these. And again, their wall crossing only involves sheaves. All right. So that's good. And that gives us control. That means the rank never increases. It doesn't quite mean the rank decreases, which would be good for an induction, because the rank might stay the same and the other destabilizing piece might be rank 0. And that does happen. So we need a bit more control in that case. And that's given by the discriminant. So the discriminant's this topological quantity here. And this always decreases. Whenever you have a semi-stable thing splitting into pieces, the discriminant of the pieces is always strictly less than the discriminant of the original thing. And it can't drop below 0. That's a Bogomolov type inequality again. So what you find is that all these pieces, all these corrections actually are smaller in the sense of either the rank or the discriminant. And so you do a double induction on rank and discriminant, and you turn that formula that I got from crossing the Joyce-Song wall into this formula where I've turned, I've taken this quantity up to the large volume limit. I've taken W up to infinity. I've taken this quantity down to 0, down to below the BG line, so where there can't be any stable objects, so I get 0. Same with this one, I've taken it up to the large volume limit, and then I've got corrections, and I've got corrections to my corrections, but we have control on all of those. They either have lower rank or lower discriminant, so by an induction, we've already dealt with those. Those can already be expressed in terms of DT invariance of lower rank. And then we do this final wall crossing from tilt stability to Giesecke stability. And so what we end up proving the results, so that DT invariance in rank R are written in terms of DT invariance of lower rank. Okay, and then the very last thing, do I have time? I have 1 minute. So finally, I want to go from rank 0 to rank -1. So we go one further step, we just do the same as before. Again, we twist everything up, we make it all positive, we take a section, and then we replace E now by this complex of sheaves. So we don't take the co-kernel anymore because it's not an injective map anymore. E has rank 0. So this is not an injective map of sheaves. So we don't want to take kernel or co-kernel. We just take the whole complex. We take the kernel. All right. So that's a rank -1 complex because it's got degree 1. Sorry, rank 1 in degree -1. And this rank 0 piece. And so we study stability of these rank -1 complexes, these two-term complexes. They live in Bayer-Macrì Toda's abelian category, so we can do the same analysis as before. The Joyce-Song wall gives us a relation just like before, and just like before, all we have to do is control all the corrections, all the shrapnel that comes off as you go over these walls. And a similar but different analysis shows that now, instead of getting control by showing that everything that comes off is a sheaf, what we show is that everything that comes off is either a rank 0 sheaf or another rank -1 complex. So nothing worse happens. You don't get like rank 1 sheaves and rank -2 complexes or anything like that. And instead of the rank dropping, or sorry, instead of dealing with the discriminant, what we deal with is this degree. So these rank 0 sheaves have a degree, roughly speaking, you take their support and take the degree of the support with respect to the hyperplane. This always drops. This is always less than the degree of the support of the thing you started with, like this E here. So again, you get an induction. Okay, and that allows us to prove that it's just the same as before using this new control. What you end up showing is that your count of rank 0 sheaves E can be written in terms of a count of rank -1 complexes F. And then finally, we can turn these rank -1 complexes into rank 1 sheaves by shifting them and taking their derived dual. This has rank 1, and after a further wall crossing, it becomes a stable pair. Is that true? I think it already is a stable pair. I think I've gone mad. Well, it depends I guess it depends what stability condition I started with. Okay, let's pretend I'm correct. Maybe Soheyla can tell us in a minute. And then after further wall crossing, these stable pairs, stable pair, I didn't tell you what a stable pair is. Anyway, it's something that's very close to an ideal sheaf. And after a further wall crossing that was studied 10 years ago by Bridgeland and Toda, it becomes an ideal sheaf. They'd already handled this wall crossing. And so what we end up with is a count of ideal sheaves and therefore rank 1 DT theory. So in this case, what we end up with is a universal formula relating rank 0 invariants, or therefore any rank of invariants, to rank 1 invariants. Okay, so I stop there.
Okay, let's thank the speaker for the excellent talk. And is there any question?
Yeah, I have another question. So you showed us the picture where you have this the Bogomolov wall under which you have no stable objects, right?
Yeah.
And somehow, in general, that it's not always clear whether that area exists at all. It could be empty. Is this sort of that you choose n large enough and then it becomes bigger?
Yeah, exactly.
Okay.
Yeah, that's exactly correct. For n large enough, there's something underneath it. Yeah. And that's why you get finitely many walls here, right? You don't have walls limiting to, if this BG wall just touched the parabola, then you could have infinitely many walls, I think, approaching the BG wall. Is that correct, Soheyla? Did not?
Yeah, that could be.
Here? Yeah.
I'm not Soheyla, but yeah.
Hello. Hi. So yeah, exactly. So for large n, we have this sort of behavior that the BG wall is high enough so that we can control all walls above it.
Yeah. Navid, did you have your hand up?
No, I was that was a clapping hand.
Oh, okay.
I should have thought.
Are there more questions?
Hi, Richard. Can I ask a question?
Yeah, of course.
So you mentioned virtually birational when you were speaking about the wall crossing, and someone asked about one-by spaces. Can you make this virtually birational more precise, or it's not there yet?
Yeah, Toda is making this precise, or has made this precise. Let me see. Okay, I guess the easiest way to say it would be, let's pretend, this is not far from the truth, let's pretend that our moduli space is embedded in some smooth ambient space in which it's the critical point of a function. It's the critical locus of a function on that smooth ambient space. And then what we're doing is you're doing some birational transformation to that ambient space. And then we're imposing the critical, and that the function extends to a function on the birational modification, by the way. And then you're taking critical locus on both sides. And that's your change in moduli space. So it might not be a birational change in moduli space, but it is a birational change on the ambient spaces. And it's a kind of a birational change in the sense of derived geometry, but not of actual geometry. So it's the kind of thing, that Ed Siegel does, right? It would be like an LG model. You do a birational transformation on the ambient space, but then when you take the critical locus of the LG functional or whatever, then you needn't get a birational transformation. But you do get a relationship between the category of matrix factorizations. And that's what Toda is globalizing, because what I just said is really only the local model. The global model is more complicated. You have to glue these things. Did that make any sense?
Yeah. May I ask a question about where is the Bogomolov-Gieseker's stability condition that Chen for each stage 3 used here? Like for example, there are other Calabi-Yau 3 folds which probably satisfy certain weaker version of the BG3 stage 3 inequality. Will that also work?
Maybe I'm not sure I fully understood the question, but let me just say something. Firstly, all our results work for any threefold, except that we're using this wall crossing formula all the time, and that was why we needed Calabi-Yau 3. So Joyce today on the archive put a wall crossing formula for Fano threefolds. So it seems likely that for Fano threefolds, where you can also define DT invariants, that all of this more or less goes through. But now, what your question was about other threefolds which don't satisfy BG, or?
Yeah, for example, like certain weaker form of the BG inequality, like
yeah.
3.
Yeah, so of course we don't need the full BG, we only need a weaker version. And yeah, Soheyla tells me she's confident that the version written down, for instance, in Bayer-Macri's ICM paper is probably true. And, you know, one of you guys will prove it soon. Is that true?
Yeah, well, probably I've said that it's probably enough for our results.
Okay.
So, yeah.
I see.
Anyway, I think what you should think is that this BG inequality, of course, Benjamin proved it isn't true in general, in absolute generality, but some weakening of it is enough for us and will be true. And, you know, I'm quite confident it'll all be fine.
I see. Thanks. Are there more questions? Okay. If no, we can move to the gather town. Okay, let's start recording.